With this system of differential equations, we've got some vector function x. We don't know what the function is, but we know that its derivative is this coefficient matrix times vector x. And any thoughts on how we could start solving this? Is there any idea what the solution might look like? In general, if we just have x prime equals some matrix times x, what would you expect the solution to look like there? Has the instructor provided any methods for dealing with a problem like this?
He just said that just to go ahead and start looking for the eigenvectors. And
yeah, eigenvectors and eigenvalues is a good start. Sorry, what was that?
And also to use that to find the characteristic equation.
Yeah, I mean, that's going to be one step in finding the eigenvectors. The reason those eigenvectors are important, though, is that if you want to solve this differential equation, if we go back to differential equations of just like a single variable that we saw earlier, like let's say you had just, let's say y prime equals some constant times y. If this is just a scalar equation, what's a function you already know whose derivative is just a constant times the function itself?
Exponential.
Right, an exponential function. Specifically, y equals e to the at. And also times a constant, which works out to be y sub 0. If you plug in 0 to t, then this constant is just 1 times this constant equals the initial condition, y at time 0. So since this is also derivative of a function equals a constant times the function itself, we can expect a somewhat similar type of solution. In fact, we can make a guess that it's also an exponential function. So what I typically do here is make the guess that x is an exponential function, let's say e to the rt, where r is some scalar, times some vector v. Because the thing is, x can't be a scalar function, x has to be a vector function here. So we guess that x is an exponential function times some constant vector. And how do we check if that guess actually works or not?
Find the derivative.
Yeah, we need to find the derivative. E to the rt just becomes r e to the rt, and then v is a constant, so it's still just times v. Now, if we plug all that in, let's see what we get. X prime is r e to the rt times v. That has to equal a, the coefficient matrix, times our guess, e to the rt times v. So that means this guess works as long as this equation is true. Also, what can we get rid of in this equation?
V.
We can't get rid of v because v is a vector and you can't divide by a vector. But what could you divide both sides by?
E to the rt.
Yeah, we can divide both sides by that exponential. Divide both sides by e to the rt. Those cancel out. So we're left with matrix A times vector v must equal scalar r times vector v. So this guess works as long as the matrix times the vector equals a scalar times the same vector. And what do we call that? What do we call it when a matrix times a vector equals a scalar times the same vector?
The eigenvalue?
Yeah, this is the very definition of an eigenvalue, that the matrix times the eigenvector equals the eigenvalue times the same eigenvector. So what we've just found is that this guess works as long as v is an eigenvector and r is the eigenvalue associated with it. So let's rename that to lambda, just because that's what we usually call eigenvalues. Ultimately, this guess works as long as lambda is an eigenvalue of the coefficient matrix, and V is the eigenvector associated with it. So with that in mind, this guess should work. So that's the general format we should expect for solutions to a system of differential equations. And that's why we need to find the eigenvalues and eigenvectors. As long as we can find the eigenvalues and eigenvectors of this matrix, we can just put them together in this format. And that should be solutions. Any questions on that so far?
And this is the fundamental solution?
Each one of these would be a fundamental, well, it's not so much one solution being a fundamental solution. We talk about a fundamental set of solutions. So this would just be one solution, but a matrix is probably going to have multiple eigenvalue eigenvector pairs. So if we list out all of the eigenvalue eigenvector pairs for that matrix and put them all in this format, then we'll have a fundamental set of solutions.
I think this example has a set of two solutions.
Sorry, what was that?
I think this example has two solutions.
Yeah, like a 2x2 matrix, you can expect up to 2 eigenvalues and 2 independent eigenvectors associated with them. If it was 3x3, we'd expect 3 eigenvalues and up to 3 eigenvectors. Or up to 3 eigenvalues, up to 3 eigenvectors. So with that in mind, let's try finding the eigenvalues and eigenvectors of this matrix. We want A times V to equal lambda times V. So how do we actually find V and or lambda here? How do we calculate those eigenvalues and eigenvectors?
Subtract the multiple of the identity matrix. Just use lambda.
Yeah, because if we subtract lambda V from both sides and then factor out V, we're left with A minus lambda I times V. Because you can always throw in an extra times I to any matrix or vector. And we need to, because A minus lambda on its own doesn't work. That's a matrix minus a scalar. But A minus lambda I, that's a matrix minus a matrix, so that works. And what do we need to assume about A minus lambda in order for this to have more than just a trivial solution?
It's linearly independent.
What do you mean by linearly independent?
I mean the determinant says it's not 0.
Yeah, we want or actually we do want the determinant to be 0 here. Because the thing is, if the determinant is non-zero, then this matrix is invertible. And if the matrix is invertible, we can multiply both sides by inverse. Like let's say you have, let's just call this matrix B. B times B equals 0. If B happens to be invertible, we can just multiply both sides by B inverse on the left. That way B inverse and B cancel out, so we just get B equals, and what's B inverse times the 0 vector?
0.
Right. Which means if this matrix is invertible, then V equals 0 is the only solution. And V equals 0 does work. If you plug in 0 vector for V, you get A times the 0 vector equals lambda times the 0 vector. That's true, but it's not very useful. It's a trivial solution. We want the non-trivial solutions. We want eigenvectors that are not just the 0 vector. So we need to assume that 0 is not the only solution, which means we need to assume that A minus lambda I is not invertible. We want A minus lambda I to be a singular matrix. So what should we set the determinant equal to? If we want to make sure the matrix is not invertible, then the determinant has to be.
The determinant has to be.
Generally, we're going to need the determinant to be 0 here. If the determinant's non-zero, that means the matrix is invertible, and that means we get only the 0 solution. So in order to get more solutions, we need the determinant to be 0. So we can start with that assumption. We can just assume that we're dealing with a lambda value that makes a minus lambda I have 0 as the determinant. In fact, you can basically use this as a starting point. Anytime you're trying to find eigenvalues and eigenvectors, you can skip these. I mean, it's good to know these steps to understand why the determinant needs to be 0 and what you do with it next. But when you're actually trying to find the eigenvalue, this is the starting point. You take the determinant of a minus lambda I, set that determinant equal to 0, and that gives you a characteristic equation you can solve for lambda. So let's try that out with this matrix in particular. We write out a minus lambda I, which basically just means we're subtracting lambda from everything on the main diagonal, because lambda I is lambda of 0, 0, lambda. So we get 2 minus lambda, -1, 3, -2 minus lambda. We're taking the determinant of that and setting that equal to 0. So let's try that. Since it's 2 by 2, we can just multiply across the diagonals and subtract. So for instance, this diagonal, we've got 2 minus lambda times -2 minus lambda. And then for the other diagonal, we've got -1 times 3. We subtract those, set the result equal to 0, and let's see what we get. Multiplying this out, 2 times -2, +2 lambda minus 2 lambda cancels out, plus lambda squared. And then minus 3 becomes +3. Reducing to lambda squared minus 1 equals 0. So what are our possible lambda values here?
Plus or minus 1.
Yeah, lambda is plus or minus 1. And in this case, you can get that by factoring or by adding 1 and then taking the plus or minus square root. Either way, we've got 2 eigenvalues, 1 and -1. Any questions on that so far? So we're going to make a note of the eigenvalues up here. We have, and I'm just going to arbitrarily call one of these lambda 1, the other one lambda 2. Let's say lambda 1 is +1, lambda 2 is -1. Doesn't matter which is which, just pick a labeling system and stick with it. And at this point, now that we have the eigenvalues, let's backtrack to the last time we saw V. We were assuming that a minus lambda I times V equals 0. We now have values for lambda. So if we plug those in, let's say let lambda equal +1. If we write out a minus lambda I using +1 for I, that means we're just subtracting a minus 1i. So a minus lambda I is going to look like 2 minus lambda, -1, 3, -2 minus lambda. We're subtracting lambda from everything on the main diagonal, but lambda here is 1. And we want that matrix times the eigenvector to equal the 0 vector, so we can think of this as an augmented matrix. A minus lambda I augmented with the 0 vector. If we row reduce that, we should be able to get the eigenvector. We can start by simplifying a bit. 2 minus 1 is 1. And then -2 minus 1 is -3. So how can we row reduce this matrix if we want to get this all the way to RREDF?
We can subtract 3 times the first row from the second row.
Yeah. And in fact, that should just cancel out the second row entirely. We're just going to get a row of all zeros, which is good. We should expect a row of all zeros because we want the result to be infinitely many solutions. And to write out those infinitely many solutions, let's say we call our eigenvector, let's just call it A, B for now. That means we've got an A column and a B column. If we write out this row as an equation, what would that equation look like?
A minus B equals 0.
Right. solve for the fixed variable in terms of the free variable, we get A equals B. That means back in our eigenvector, we can replace A with B, factor out B, and what's left?
1.
So that is our eigenvector, 1, 1. And of course, any scalar multiple of that will also work. So for instance, 2, 2, or 73, 73, or negative square root of 2, negative square root of 2. The important thing is that it's a multiple, a scalar multiple of this vector. So let's call that our eigenvector B1. And you can always check your work on that by multiplying it by the original matrix. Original matrix times 1, 1 should equal 1 times 1, 1. You can just multiply the original matrix times the eigenvector, and also separately multiply the eigenvalue times the eigenvector. You should get the same result. Let's try the other eigenvalue. We've got -1. So we're going to take our original matrix and subtract -1 from everything on the main diagonal. In other words, add 1 to everything on the main diagonal. And simplifying that, we've got 3, -1, 3, -1. So what's going to happen to this when we row reduce?
It's going to cancel out. We'll get 0.
Yeah, subtract row 1 from row 2, and row 2 is just going to cancel out again, which again, we should expect. We want infinitely many solutions here. And again, if we think of this as A and B, we can write out our equation, 3A minus B equals 0. And formally, we would usually solve for the A as a fixed variable in terms of B as the free variable. But I think in this case, it'd be easier to solve for B instead. Solve for B, you get B equals 3A. So we can just replace B with 3A. Factor A out of that, and what's left?
1 and 3.
So that would be our other eigenvector. The eigenvector associated with -1.
And we can use our guess, like what it should look like, and use the eigenvalues and eigenvectors.
Yeah, exactly. Now that we have all the eigenvalues and eigenvectors of this matrix, we can just insert those into the format that we guessed earlier that worked. The e to the eigenvalue t times the eigenvector. So let's try that. Now that we have the eigenvalues and eigenvectors, we can formulate our solutions. So we could write this as, let's say, x1 is e to the lambda1t times vector v1. So in general, we're assuming that the solution is x. Let's say the nth type of solution is e to the lambda nt times vn. So we could use x1 using the first eigenvalue eigenvector pair, x2 using the next eigenvalue eigenvector pair, and so on. And then for x2, we've got e to the -1t times this eigenvector 1, 3. So those two, x1 and x2, this solution and this solution, they're both solutions, and together they would form a fundamental set of solutions in the sense that they're linearly independent. Any questions on that so far?
I know that I have some examples where you get a complex eigenvalue, and
yeah. If the eigenvalue is complex, then you would use the Euler's formula as we did in chapter 3 to turn it into sine and cosine. Also with this one, we've got two solutions. How do we put those together to make all the solutions?
You can multiply that with a constant like C1 and C2 and add those.
Yeah, if we just have a constant times each one. So basically just linear combinations. This also ties into the idea that any scalar multiple of an eigenvector is still an eigenvector. So we get this. Would it still work if we put e to the negative t times 1, 1? Not in this case, because this eigenvalue, this negative 1 eigenvalue is specifically associated with this eigenvector. And the eigenvalue positive 1 is specifically associated with this eigenvector. So you could change the order. You could call this x1 and this x2, but you don't want to split up which eigenvalue is attached to which eigenvector. Any other questions on that idea so far? And this problem is specifically asking you also for an idea called a fundamental matrix. A fundamental matrix is basically just putting together these vectors, but in a way that makes it into a matrix. Specifically, the idea of a fundamental matrix is that we want a matrix, let's say capital X, which is a function of t. We're basically going to be combining these vector functions. Just note that this one, for instance, if you actually multiply this out, you get e to the t, e to the t. That's a vector function. And likewise, this one, you multiply this out, you get e to the negative t, 3e to the negative t. These are both vector functions. The idea is we want to be able to create a matrix consisting of those vector functions. And we specifically want to be able to just multiply it by any initial conditions to immediately get the actual solution. So for any initial conditions, and the initial conditions would typically take the form of x of 0 equals x naught, where you know what you get if you plug in 0 for t. The idea is we want the specific solution to be able to be found really easily. The idea is all you need to do to find the specific solution is take your fundamental matrix and multiply it by the initial value. Because the thing is, the initial value is ultimately just going to determine the values of C1 and C2. But we want to be able to set this up so that we don't even need to solve for C1 and C2. We want to be able to find essentially a transformation matrix that immediately converts the initial condition, whatever it is, into the specific solution. Any questions on that so far? And have you seen anything about how to find that initial condition, that fundamental matrix?
My professor, Chandler, he just went over that today. So I think we replace the matrix, sets the initial conditions, so we would get a identity matrix and solve for that.
Yeah, one way is to we specifically want one where if the initial condition is, if you plug in 0, you just get the identity matrix. Because if you did plug in 0 here, if you plug in 0 for t, the idea is x of 0 is x naught. So we would like x, the big X of 0, the fundamental matrix at time 0, to be the identity matrix. So we need to be able to find ways of combining these two vectors, e to the t, e to the t, and e to the negative t, 3e to the negative t, in such a way that if we were to plug in 0 for t, we'd get the identity matrix. So let's try that out. And the idea is in that big X of t matrix, each column is going to be a linear combination of those individual vectors. Let's say ax1 plus bx2 as a column, and then some other linear combination, cx1 plus dx2 as another column. The idea being that we want something where if we were to multiply this by the initial conditions, we'd get a new linear combination of x1 and x2 that works for those initial conditions. But one thing we want here, we want the columns to become the columns of the identity matrix if t is 0. And what are the columns of the identity matrix?
1, 0, and 0, 1.
Yeah, we want these columns to turn into 1, 0, and 0, 1 when t is 0. So this is one way we could do this. We can essentially treat this as an initial value problem anyway, a standardized initial value problem where we get 1, 0 or where we get 0, 1. So let's try this out. Let's assume that we have some linear combination of x1 and x2 such that when we plug in 0 for t, we get 1, 0. And also some other linear combination where when we plug in 0 for t, we get 0, 1. So let's try this. Let's assume that a times x1 of 0 plus b times x1 of 0 is 1, 0. However, if we plug in 0 for t, what happens to the e to the zeros?
They just go to 1.
Right, which means we just get a times 1 times the eigenvector plus b times 1 times the other eigenvector. We're basically looking for a linear combination of the eigenvectors that adds up to 1, 0. So let's try that. In this case, we should be, since this is essentially a system of equations, we should be able to just combine the eigenvectors, 1, 1, 1, 3, augment with 1, 0, and then row reduce. And what's left should be the values of A and B. However, we're going to have to do this all over again with the other eigenvector, or the other result. We also want 0, 1. So let's augment the matrix twice. Let's have 1, 1, 1, 3 augmented with 1, 0. And keep in mind these columns are just the eigenvectors. And also 1, 1, 1, 3 augmented with 0, 1, because we want both results. In other words, we're just augmenting with the identity matrix. And when we row reduce, what are you usually trying to find when you row reduce something like this? If you augment a matrix and the identity matrix and row reduce, that's usually the procedure for finding what? Yeah, the inverse. Ultimately here, we're just finding the inverse of the eigenmatrix, the matrix consisting of the eigenvectors as columns. So we want to find the inverse of this. And what process could you use here? How could you find the inverse of this matrix? Either by row reducing or some other process. Could we row reduce this? Like I'm noticing this pivot here is not alone in its column. How could we use this to get this pivot to get rid of the 1 under it?
You just subtract it from the second row.
Yeah, if we just subtract row 1 from row 2, that's going to give us 1 minus 1, 3 minus 1, 0 minus 1, 1 minus 0. And then we'd like this pivot to be a 1. So I'm going to multiply this row by 1/2. So 1, 1, 1, 0, 0, 1, negative 1/2, positive 1/2. And then we also want to use this 1 to eliminate the 1 above it. So let's also subtract row 2 from row 1. And let's see what that gives us. 1 minus 0, 1 minus 1, 1 minus minus 1/2 is 1.5 or 3/2. 0 minus 1/2 is negative 1/2. And then second row exactly as is. So that means these columns are the values of A and B and the values of C and D. And yeah, since it's 2 by 2, you could also use the shortcut of 1 over the determinant times, and then flip these numbers, take the opposite of these numbers. So that would also work. Ultimately, we just need the determinant of this eigenvector matrix. So let's see what we can do with that. Now that we have these values, we can basically treat these as the values of A and B and C and D. So we'll have 3/2 times this vector plus negative 1/2 times this vector. So let's try that out. So the first column was 3/2 times this eigenvector, which was e to the t, e to the t, plus negative 1/2 times the second eigenvector, the second solution, which was e to the negative t, 3e to the negative t. And then for the second column, we take a look at the second column of coefficients, the negative 1/2 and the positive 1/2. So negative 1/2 times the first solution plus positive 1/2 times the second solution. And these should give us the columns of the fundamental matrix. So let's try this out. First column, we can just multiply this. 3/2 times e to the t plus negative 1/2 e to the negative t. And then 3/2 e to the t minus 1/2 times 3, so 3/2 e to the negative t. So that will be the first column of our fundamental matrix. And then the second column is going to be these combined. So top row, negative 1/2 e to the t plus 1/2 e to the negative t. And then bottom row, negative 1/2 e to the t plus 3/2 e to the negative t. So those are the columns of the fundamental matrix, and now we can just augment those together. Any questions on the work so far before we put those all together?
Once you put those together, it should give you the identity matrix if you set t to 0.
Yeah, because if we did set t to 0, all of the e to the whatevers would just become 1. So we'd have 3/2 minus 1/2, that's 1. 3/2 minus 3/2, that's 0. And then second column, negative 1/2 plus 1/2, that's 0. Negative 1/2 plus 3/2, that's 1. So this becomes 1, 0, 0, 1 if we plug in 0 for t. That's a good way to check the work afterwards. Any other questions on the math there so far? Let's put all this together. For our fundamental matrix of the solution. So the first column is going to be this whole thing. And then the second column will be this whole thing. So this is our fundamental matrix. And it still represents all the information that was in our specific solutions from our fundamental set of solutions. We're just combining it together so that each column of this matrix is some linear combination of those solutions. And moreover, that if you were to plug in 0 for t, you would specifically get the identity matrix. And for a fundamental matrix, you could get any linear combination of the columns. Like we could have just taken, maybe the first column could just be e to the t, e to the t, and the second column, e to the negative t, 3e to the negative t. If we just wrote that out, if we just wrote e to the t, e to the t, e to the negative t, 3e to the negative t, this would also count as a fundamental matrix. But we specifically want the fundamental matrix where if you plug in 0 for t, this turns into the identity matrix. This one wouldn't have that property, so it's not as useful. And the reason why this one in particular is useful, the fundamental matrix that turns into the identity matrix when you plug in 0, it's a huge pain to set up. But once you've got it, you can use this to almost instantly find a specific solution to any initial value problem using this differential equation. Because in general, the solution is going to be x of t equals this fundamental matrix, big X of t, times the initial value, x of 0. Because multiplying this out, if you take this matrix times a constant vector, you're just going to get linear combinations of the columns. Linear combinations of those columns is exactly what we had in our general solution in the first place. But by setting it up in exactly this way, we don't even need to solve for C1 and C2 anymore. If you plug in any initial condition at all and multiply this out, then it will automatically fill in the constant coefficients you need. For example, I think in problem 2, let me look that up. Yeah, problem 2 gave us an initial condition. Specifically, the initial condition was x of 0 equals 2, negative 1. So that means to find the specific solution, if we had our general solution written down like this, we'd have to plug in 0 for t, set this equal to 2, negative 1, and solve for C1 and C2. But now that we have the fundamental matrix, all we have to do is multiply the fundamental matrix by 2, negative 1. And note that that just turns into 2 times the entire first column plus negative 1 times the entire second column. So multiply that out, and we get 2 times the entire first column, which becomes 3e to the t minus e to the negative t, 3e to the t minus 3e to the negative t, plus negative 1 times the entire second column. So that'll be positive 1/2 e to the t minus 1/2 e to the negative t, positive 1/2 e to the t minus 3/2 e to the negative t. And then you could combine those together, just lump those into one vector. And then combine like terms. If we've got a 3e to the t plus 1 more half e to the t. So 3.5 e to the t. And then negative e to the negative t minus 1/2 e to the negative t. So minus 1.5 e to the negative t. And then 3e to the t plus another 1/2, that'll be 3.5 e to the t. Minus 3 minus another 1.5 would be minus 4.5 e to the negative t. So that would be our specific solution. And then it might be useful to split that up further into 3.5 times e to the t, plus maybe negative 1.5 times e to the negative t, 3e to the negative t. So you still get linear combinations of the eigenvector times e to the eigenvalue t. It's just that writing out the fundamental matrix skips all the work of solving for C1 and C2. And of course, like I said, setting up the fundamental matrix takes a lot of work in the first place. But where this method really shines is if you have one differential equation system and lots of different initial values. Like let's say you had also this differential equation system and another initial condition, and the same system of differential equations and another different initial condition. Maybe you've got one differential equation, but lots of different initial conditions. Instead of having to solve for C1 and C2 over and over and over again with each initial condition, you can just find the fundamental matrix once and then multiply that by any initial condition you want. The fundamental matrix is essentially a linear transform that turns any initial condition directly into the specific solution for that initial condition. So that's really, I think, why fundamental matrix is a big deal. In most cases, I would usually prefer to use this method, to just find the eigenvalues and eigenvectors and write out C1 times e to the eigenvalue t times eigenvector plus C2 times e to the other eigenvalue t times the other eigenvector. And maybe more terms if you have like a 3x3 matrix or larger. And for most purposes, that works well. But if you're going to be dealing with lots of different initial conditions for the same system of differential equations, it's worthwhile to find the fundamental matrix once and then multiply it by any initial condition you want. And the fundamental matrix also shows up in some other formulas as well. So it can sometimes be useful, especially if you're dealing with a non-homogeneous system of differential equations. Any other questions on
I think that like the way my professor showed it, like that's the first way he told us to solve for initial condition. Like he hasn't really went over like doing it the other way using like C1 e to t plus C2 e to negative t, to use that with their initial condition to find the specific particular solution.
Yeah, either way would work. You could just take this format, plug in 0 for t, and then set it equal to the initial conditions, and then solve for C1 and C2. You'll get the exact same result. It's just a different way of solving it. I tend to find this approach, the idea of linear combinations of e to the eigenvalue t times an eigenvector, I find this approach a little more useful, or I should say a lot more useful, for getting a more intuitive understanding of what's actually going on. That you really just have this direction on like an XY plane. You've got the 1, 1 direction, and that's growing outwards to infinity because e to the t is exponential growth. But you've also got this direction, 1, 3, so like 1 to the right, 3 up. And that's decaying towards the origin along that line because e to the negative t is exponential decay. So I find that writing it out like this makes it a lot easier to understand what's going on. But putting it all together in the fundamental matrix can be more useful if you want to solve lots of initial value problems at once. They both work, just different ways of writing the same result. Any other questions on that? All right, then I will see you next time.